So let's just get started with the semiconductor in equilibrium, because now we know some of the most important concepts which we require to understand the physics in a semiconductor. All right. Oh, sorry. So we have some of the statistical laws. Now, what are these statistical laws? Statistical laws explain the statistical behavior of particles. Okay, see, for example, if we have a space where some molecules, gas molecules or any other particles are confined, there are ample number of particles. Now, as a system, we are not concerned about the behavior of an individual particle. So that is, we are not concerned about the behavior of individual particle, but however we are interested in behavior of particles as a group, isn't it? Right. So there are some laws governing the behavior of these particles in any system, right? Okay, now let us go to the types of statistical laws which we have. We have the very famous Bose-Einstein law, we have the Maxwell-Boltzmann, we have the Maxwell-Boltzmann law, we have Bose-Einstein law, and we have the very famous Fermi-Dirac distribution function. Okay, so all the three laws are regarding the behavior of the particles in any system. So these are the three statistical laws governing the behavior of particles in any system. That is Maxwell-Boltzmann. It is used for all of the classical particles, Bose-Einstein, and Fermi-Dirac distribution function. The details are given in the book. And what here we are more interested for the quantum mechanics. We are more interested into the Fermi-Dirac distribution function. Fermi-Dirac distribution function says that if we have n number of particles, these particles will be indistinguishable. We cannot distinguish one particle from the another particle, and only one particle is allowed in one quantum state, right? It obeys Pauli's exclusion principle, and the distribution function is given by this expression, and the spin is spin can be plus or minus 1 by 2, and this Fermi-Dirac distribution applies to an electron in a crystal. Alright, now just a bit of explanation on the Fermi-Dirac distribution function. That is, if we have n particles, as I said, that these are indistinguishable in the Fermi-Dirac distribution function. So that is, you have n number of electrons, and these are the allowed quantum states, and you know any of the electron among these n number of electrons can occupy these quantum states. So using some of the probabilistic distribution, using some of the mathematics, we can find out the most probabilistic distribution of these electrons among these quantum states, right? And after a bit of analysis, we get the expression that is f of E, that is the distribution of the electrons in the system, is given by the total number of electrons divided by the density of states, that is the number of electrons per unit volume, per unit energy, and the density of quantum states, or the number of quantum, because density of states is actually the number of quantum states per unit volume, per unit energy, and the expression comes out to be this thing. The solution is given in the appendix J of it's given in the appendix J of Donald A. Neiman, right? Yeah. And so f of E also, it's justified to say that f of E gives us a so f of E also gives us the ratio of the filled states to the total quantum states. Right. Now there are EF is a constant value, and it's EF is a constant value, and EF is a constant value and is the Fermi energy of the system, right? EF is known as the Fermi energy of the system. Now we can make the comparison of E with respect to EF, and we just need to analyze this Fermi-Dirac distribution function, because from this very expression we'll not be able to analyze it graphically. Now we'll try to assume some of the conditions. Let us suppose case first for temperature equals to 0 Kelvin. Okay. Now when temperature T is 0, f of E, will simply substitute this absolute temperature as 0. It will be 1 upon 1 plus exponential E minus EF upon 0. So it appears that this will turn out to be 1. Yeah, because 1 upon 0 will be infinity, and exponential of infinity will be infinity, and then 1 upon infinity will be 0. But we have two more cases here, depending upon the value of the energy, that is E lesser than EF and E greater than EF. Now when E is lesser than EF, for energy E less than EF, we have f of E equals to 1 upon 1 plus exponential of minus some value, isn't it? Some minus difference upon infinity. Let us say that n is the difference between the two. So the second term turns out to be minus infinity. So it will be exponential of minus infinity is 0. So this term becomes 1 divided by 1 plus 0. So that is 1. And for energy E greater than EF, f of E is equivalent to 1 divided by 1 plus exponential of some plus n upon 0. That is, it becomes 1 divided by 1 plus exponential of plus infinity, that is 1 by infinity, which is 0. So now we have two conditions for when the temperature is 0. Now let us take case second. Let us take case second. Yeah. Let us take now second case for temperature greater than 0, that is for a non-zero temperature. We'll analyze what happens theoretically when temperature is not equivalent to 0 or when it starts increasing, because the electron energies will start increasing. Here we'll realize what will happen to this mathematical function. All right, so yeah, when temperature is greater than 0, your f of E, for again the two cases, that is E greater than EF or E lesser than EF, yeah, so it will be f of E as 1 upon 1 plus exponential E minus EF upon some non-zero value, because it's k into t. Now since it's non-zero, we have to realize this condition for how many cases? E less than EF, E greater than EF, and E energy equal to EF. Okay, so when the energy E is less than EF, our f of E will be 1 upon 1 plus exponent term E minus EF upon KT. Alright, so this will be some kind of a 1 plus 1 upon exponential of, because E is lesser than EF, so it will be some kind of a negative number. It will be some minus n. Now it will not be divided by 0 because the temperature is finite. Then this term will be lesser than 1, so this will be almost equal to 1. Then again, for the another case where E is greater than EF, we'll have 1 plus exponent of plus n, right? So the denominator will be greater than 1, so it is almost equal to, f of E will be almost equal to less than 1, isn't it? Its value will start decreasing, yeah, because this denominator will be a bigger number. Yeah. Okay, so this is E greater than EF, this is E lesser than EF. Now when E is equivalent to EF, our f of E will be 1 divided by 1 plus exponent E minus EF is simply 0. So it is 1 divided by anything raised to the power of 0 is 1, and this comes out to be the value of 1 by 2. Okay, now we have two conditions for temperature equal to 0, for temperature greater than 0, and the different cases for the values, the comparative values of the energy, whether the energy is greater than EF or whether it is lesser than EF, right? Now let's try to sketch it up. So on the one side, okay, let me use a ruler. On one side I'll plot f of E, and on the other side I'll plot energy, right? So the first thing, and this is the graph for, okay, all right. Now this thing is your energy E, oh sorry, this is your energy E, this is for T equals to 0 Kelvin, this is for T greater than 0, okay, and this is our f of E. Okay, this is again our f of E. this is 0, let us say, and this line point is 1. Now let us say along the energy this point is E of f, and along the energy same here, this point is E of f, starting from 0 to some higher value. Now for the temperature T equals to 0, when energy E is lesser than E of 1, the Fermi-Dirac distribution function has a value of 1. So it's like this, we plot it like this. Now when energy E, which we see from here, when energy E is greater than EF, alright, so the f of E has a value of 0. So when energy becomes greater than E of f, this f of E has a value of 0. So this is how the Fermi-Dirac distribution function looks when T is equivalent to 0. Now the second case is, which we did for T greater than 0. What did we say? Let me first plot the distribution function for T equal to 0, okay? And this is one value, 1, and this one is 0.5. Let's say it is okay, so this is 0.5. okay, now what is the mathematical analysis say? It says that for temperature greater than 0, when the energy E is less than EF, our Fermi function is almost equal to 1. When it is greater than EF, it is less than 1, and when it is equal to EF, it is 1/2. So 1/2 is this line. So that is our Fermi, this point from here is E less than EF, and this scale is E greater than EF. So if we plot it, it's right, and at E equals to EF, it has a value of 0.5. So as temperature increases, it falls from here and it goes like this. All right, so this is for the temperature T equals to 0. This is for temperature T1. T1 is greater than 0 Kelvin. All right, now if you are going to increase the temperature, what will happen? I'll use another color where that we have a temperature T2. So it is like this only, and it will fall steeply like this. All right, so this is for blue one is for T2, where T2 is greater than T1. All right, okay, but I guess it's I'll plot it more correctly. It will be like this. Yeah. Now why did it change? See, here the value is lesser than 1 for energy greater than EF. When energy is equal to EF, it's 0.5. For energy lesser than EF, it's equal to 1. But as soon as the energy, the value of energy starts reaching to E of F, it has to obviously fall from 1, goes through 1/2, and then reaches here. So from these two analyses, we can have two definitions of Fermi energy or the Fermi level. So how do we define it? We define it Fermi level is defined as the highest occupied energy level at T equals to 0. That is, it is the energy level where the probability of finding an electron is maximum, but this definition holds only at temperature of 0 Kelvin. The second definition, so this is one definition. The second definition is, it is the energy level, it is the energy level where the probability of finding an electron is 1/2, that is, it is half, and this holds for temperature greater than 0. Alright. I hope this is clear. So further, even if the temperature goes on increasing for T2 to T3, it will be like this. Yeah, this area is going to increase, or the value is going to increase. Sharper transitions and smoother transitions, right? Alright, now this was from the mathematical point of view. Let us now try to look at it from the theoretical point of view, or what we know from the knowledge of, you see, what we know from the knowledge of the thermal equilibrium, the increase in the temperature, or the increasing energy of the electrons. So it is simply like, this is also given in your book. I'll give the reference as figure 3.3. So what has the author done? Author has drawn 5 energy levels: E1, E2, E3, E4 and E5. Alright, now the first scenario is for temperature T equals to 0 Kelvin. So you have one quantum state here. We have at E2 2 quantum states like this. We have at E3 4 quantum states. We have at E4 7 quantum states. Alright, and at E5 we may have 9 quantum states. Alright, okay, fine. Now it's simply like, maybe at temperature T equals to 0, the electrons are in their lowest possible energy states. These dots, these are the quantum states which are being occupied by the electrons. So it is like this. So these are the quantum states which are being occupied by the electron. The electrons are in the lowest possible energy state. Okay, so where would the Fermi level, lie? Fermi level would lie somewhere between E of 4 and E of 5. So this is the Fermi energy, because all of the lower levels are filled and the electrons do not have sufficient energy so that they could jump to the higher level. Okay, now let us say when the temperature increases. Now when temperature increases, the electrons which are in the range of kT, below the vacant level, will gain the energy, that is kT by Q, because these electrons which are in the lower levels require higher energy as compared to the electrons which are in the higher levels and quite nearer to the empty level. So they will gain the energy and they'll leave this quantum state and maybe they'll jump to some higher quantum state. With the result, vacant states are created here. The lower electrons may gain energy and they may occupy these states. Alright. So the distribution of electrons have changed. The change in the electron distribution among the energy levels for T greater than 0 can be observed if we plot the Fermi-Dirac distribution function, okay, which we have already done, and we have seen that probability is 1 by 2. So the probability of a state being occupied at E equals to E of F is now 1 by 2. So it gets halved. Alright. Okay. Now if we can plot this, okay, so that is if you keep the Fermi level still here, and now the probability that it occupies, because some of the electrons have left it and they have jumped to the higher energy levels, so the probability that a state is occupied automatically gets halved. So we have seen it mathematically, and here we can analyze it. So I'll write on one side T greater than 0, because this was the initial condition. The initial condition was initial condition. Alright. Okay. Now in the previous lecture we have plotted, in the previous lecture we have plotted G of E if we plot energy E and G of E like this, or if you do it in the reverse way, that is, we take G of E along Y and energy E along this. So we know that energy varies as the square of the density of states, so it will be somewhat like this. Now if the energy EF lies here, so if the energy EF lies here, what we can see is, for the temperature T equals to 0 Kelvin, what will we have? We'll have the electrons filled up to EF only. That means the electrons will be in the lowest possible state like this, and all other states which are above this, above EF, will be empty. Okay, fine. So this completes the definition of the Fermi energy. Now the second most important thing is, because in the crystals we're not only dealing with the electrons, but we are also dealing with the holes, which are equally important. So if f of E is the probability that an energy level will be occupied by an electron, then 1 minus f of E will give us the probability of finding a hole. Okay, so now we argue that when electron jumps to higher energy level, it leaves behind a hole. Alright, so this means for temperature, but it only occurs, the electron jumping occurs only for temperature T greater than 0. So if we are considering, let us plot it here. Okay, so if we are considering this is 1, this is 0, and let us say this is okay, let us say 1 by 2, 0.5 is this point. Okay, now, and this is EF, that is energy EF. Now for the energies E equals to EF, it has fallen to the probability function has fallen to 0.5. all right, and okay, so this is f of E and this is our energy E. Okay, now since this distribution function has changed for t greater than 0, how will our another function 1 minus f of E look like? We'll argue that as the electrons jump above to the higher energy levels for temperatures greater than 0, a hole is equally created. So an energy level which is at a distance of dE below EF, so that is a probability that an energy level at a distance of dE below EF being empty has the same probability as the energy level above EF at the same distance dE being occupied. So since the distribution is changing like this, our this distribution will be 1 minus f of e, that is the distribution of holes. Now what do we infer from here? We infer that 1 minus f of e gives the probability that the states are not occupied by the electrons. That means as temperature has started to increase, the lower levels have started becoming empty, shown by the green. Okay, so the empty levels are like this, and the empty levels have a very low value, and then they are increasing with the energy, and they have a maximum value like this. Okay, now these are the filled levels, red ones. These are the filled levels, because the lower levels will still be filled, and these will be empty. So the electrons which are at the top, as we have seen from this distribution of that is the the increase in the energy of the electrons, and we have seen that the upper energy levels first contribute the electrons to the empty states, and then the lower, and so on and so forth. So that means these lower energy levels remain filled for a longer time, and the upper energy level contributes to this. So the number of the holes, or the number of the empty states, would start increasing from the top levels, and then it will be maximum as energy increases. Alright, so it is that the probability of an energy level at distance dE, any distance, arbitrary distance dE, below EF being empty is the same as the energy level at distance dE above EF being occupied. So f of E and 1 minus f of E are symmetrical functions. Alright, so these are symmetrical functions. क्योंकि probability of finding a hole at a distance dE below EF is the same, holds the same probability that of finding an electron at a level of the same distance above EF, because the distribution functions are changing like this. Alright, so this is all about our Fermi-Dirac functions. And there are other calculations that the Fermi-Dirac function reduces to Maxwell's Boltzmann distribution for higher temperatures. Alright, so we simply so for very large temperatures, E for higher sorry, it's not for temperatures, it's for the energies. if E minus EF becomes much greater than KT in f of E, then f of E comes out to be 1 upon 1 plus exponential of a very large number. Okay, so this exponential term becomes much greater than 1, and this distribution function equals to exponent of minus E minus EF upon KT, and so that it looks like, if the distributions are like this, and this one is 1 upon 2, this is 1 and this is 0, somewhere here the Fermi-Dirac changes to the Boltzmann's approximation. So this one is Maxwell-Boltzmann approximation, and this here is Fermi-Dirac. So for some range of energies, Fermi-Dirac distribution holds, and when the range of energies increases, the Maxwell-Boltzmann's distribution holds. Alright, thank you. If you have any queries regarding this lecture, you may let me know. Drop me the messages, or you can even let me know your queries in the comments section given in the videos